Welcome to today's webinar from 6G-Cloud project. So from the name on the screen that you see that what is about 6G-Cloud, that we are doing service-oriented network architecture, and that is working on the cloud system for built on the cloud continuum. So today this webinar is that we dedicate for the prototype work and also demonstration from the project. We have two dedicated presentation on the PoC and the demo. But first, we will introduce the project background so that you know what the 6G-Cloud is about. And then we have a presentation from Sławomir and Roberto, and work on Warsaw University of Technology. This work on the cloud continuum framework. And then we also have a presentation from Jesús from University of Murcia, and work on the orchestration and management framework. So my name is Chen, so I'm the coordinator of this project. And I'm also work in VTT. This is a technical research center in Finland. So here is the way to ask questions. That if you have questions to ask, and you can type in the chat. So and we will first go for the presentation, and then at the end we have the Q&A session. So that is the way to run this webinar. So of course, anytime you can write questions on the chat, we will collect it. So okay, good. So let's get started. I will use several minutes to quickly introduce the 6G-Cloud project. So this is a 6 EU SMSGU project that is deal this 6G, that is a program in this EU. So this project, we mainly deal with this AI native and also cloud native system architecture for 6G. And also this architecture is working on the cloud continuum framework across different cloud. So we have altogether 12 partners that from Europe, you see here, from industry, academias, also universities, research institute, and also operator, SME. And in this project, we already started in 2.5 years ago, and now it's going to end. So the project we will end by end of October. So we already got the extension. So it has a 3 proof of concept that built from the project deal with different aspects, because we are deal with many topics here. So you will see that what aspect that we have about. So just to show you that here is the project portfolio that from this SNSG project. So there are 100 projects there. So only 3 projects that specifically deal with this service-based architecture. So 6G-Cloud is one, and also they include this origami and also unify 6G. It's all in this architectural portfolio of this project list. So and for 6G, why we need to have this 6G cloud architecture? The fund come from several needs. One is that we're trying to utilize the cloud system that run the 6G network, not only the core and also the run. That's one. So that means we need to utilize effectively the different cloud resource at the edge, at a regional cloud or at central cloud, and also we need to see that how to make a really cloud native design to this 6G network to make it end-to-end cloud native. That means that how to service-based architecture can really play the role, because that's already used in cloud network, and then how to also extend it to the this run at video access network. And with this demand that we try to manage the computation and also computation resource altogether. That means we need also a management and the resource orchestration framework to really effectively manage the resource, because that's a very complicated story right there. So this is the focus of this webinar for the management and the resource orchestration at how we build a prototype on that. And also, last but not least, this intelligence is necessary, and because 6G will be the AI native network, right? 6G network. So intelligence is a key part of it. Also, we deal with this AML framework. And here is the architecture we proposed that in the project. So it looks complicated, but it's formed by 4 building blocks that you see that in the middle is the 6G network, call and run, that we put it on service-based. So we are not going to introduce detail about this service-based run design, and because that's where it belongs to other webinar. But now the focus here is that on the top we have this morph, that is more management and orchestration framework here. This is managing the network resource and in the middle, and also the cloud resource at the bottom. That this CCF is managing. And at the bottom, we have this framework called the CCF, is a cloud continuum framework. So it's connected to the data center or the server at the edge, or even the UC terminal equipment. They also could be part of the framework. And then for the intelligent part, we have the left side here, right? So here is the architecture on the service-based run that we don't since it's not a focus today, so we just don't give detail here. So what we show here is that also you will see in the following presentation is that is morph design, right? So since they've also introduced introduction here, we just briefly introduce what it is that. So you see that we have a master service orchestrator for all compute and the communication resource, and also for different network, we call network service, that is a instance of a 6G network that could be thousands of 6G network like that, and each of these is managed by this NS, called NS director, and in each NS director also they have their own service orchestration there. Right? The key question is that how to guarantee the resource. So we need to also communicate with the cloud continuum framework here. Right? So here that we have cloud continuum framework to manage the resource, and the key concept here is the resource partition. Right? So there are more details from presentation that in next presentation there, how to have this dedicated cloud resource and dynamically allocate to one network, and that network can use the network functions run in that cloud resource and keep that service there. So and here is that how we implement it, and that's you see some part of the work is on this management framework, some part of work is on this service cloud continuum framework, but also we have this service-based this architectural service bus implementation here. So altogether, we form the full picture. So so that's the basic idea from the architectural point of view and from the 6G-Cloud project. So today, the focus is on morph and CCF, and so I'd like to hand over to our next speaker to focus on the main content for today. So let's hand over to Sławomir for your presentation on CCF.
Okay. Good morning. I just screen wrong screen. I think you can hear me now.
Yeah, good. Go ahead.
Okay. So first of all, our time is very limited today, so I will try to be quick. You can see this webinar as some kind of a guide, because we published a lot of deliverables. We have also YouTube channel that you will find our demos. So in my presentation, there will be a description of the cloud continuum and implementation of PoC-1. We have 3 PoCs in the projects. Here are the names of my team. Robert will help me in the second part of the presentation. If you will look into the project architecture, it is composed of several frameworks, and to evaluate the benefits of the approach, as it is usual, we define a set of KPIs, and as I said, 3 PoCs. Today we will present PoC-1 that has been instantiated, implemented in 2 locations. One is Warsaw University of Technology, another one is University of Murcia. That will be the next presentation. In this presentation, Warsaw has focused on the pretty detailed implementation of cloud continuum. So, looking into the architecture, the idea was to have a loosely coupled frameworks. You know, the complexity is very high of 6G. This is what is expected. So we wanted to have independent frameworks that communicate somehow, that there are multiple providers, multiple operators. So it changes the way how we talk with interfaces. And the main idea of Cloud Continuum is to use the resources that are not owned by the operator. It means public clouds, private clouds, things like that. And that way you can reduce the time to market, you can reduce the capex, and so on. We also propose that AI/ML management, it's a kind of MLOps that is common to all the frameworks, so you can think about AI native approach. Yes, we defined it nearly 3 years ago. And you see multiple resource providers in the picture, and you see an idea of resource partition. I will describe it later on. It's like a subset of resources that fulfills a specific network service expectations. So you see that there are 3 frameworks, multiple network services that can be of a different kind. And here is the very high level figure. When it jumps to the management and orchestration, there has been proposed some interesting things. First of all, typically the management of NS is external to the NS. We propose that it's following another project in which I participated a few years ago, that some management functions can be put on the NS, so you are just triggering them together with the NS. And as you see, AI functions can be placed everywhere. I mean, inside the NS, in MOV, in Cloud Continuum. This is why the AI/ML framework has to handle all this stuff. And by the way, this is only logical figure. You can just instantiate it in a more distributed way with some pipelines distributed. This is just, you know, it just shows you the flows, the generic flows, how you should play with it. And there can be multiple MOVs, multiple AI/ML frameworks, even multiple Cloud Continuum frameworks, but so far we focused only on one. Here is a CCF-oriented figure. So as you can see, we have multiple providers of cloud resources. That can be edge cloud, let's say central cloud, servers, including virtualization of the terminals. So we need a kind of a logical resource pool. We need to manage this resource pool. We need to attach new resources. So we need a lot of databases that will analyze what we got, what we can share, what is available, what is used. And we need some kind of data analytics, because we have to know what's going on with the data centers and so on. What is the idea of resource partition? Resource partition is just, try to imagine, I mean, the solution goes with a dense grid of resources. This is actually what IPCEISIS initiative in Europe is trying to do. It's nearly 4 billion euros project. So you will have a very dense resource grid. So you need somehow to select only these locations and these resources that you like, that fulfills your expectation. So it can be cost, it can be area, it can be delay between data centers, things like that. And this is the idea of resource partition that, by the way, can be also secured. So when the orchestration is coming to the play in the first phase, this is the trick. It preselects the resources, and later on it sees the resources as coming from a single resource domain. You don't see these multiple providers. That is the idea. And we have, you know, a kind of logical centralized API. We have 2 APIs, one to customers, another one to providers, so northbound and southbound. When it comes to the implementation, unfortunately, the figure is much more complex. I don't want to jump into details. You will find them in our deliverables. But just I want to show you the common blocks. So first of all, we have something that is called resource aggregation functions. Following the ETSI terminology, we have interfaces to different clouds. We have interfaces to different connectivity providers. So it's Vim and Vim. We have also gateway to terminals, and we have a kind of a controller. This is about resource aggregation functions. Then we have some analytic functions that look into some anomaly detection, reliability estimation, security dedicated engines, and so on. Then when you create this resource partition, we need to keep a database of all these resource partitions, but we went beyond infrastructure as a service, we are providing some tools with your resource partition. So it can be about prediction of resource consumption and so on. There is a toolbox and a toolset. So from the toolbox, you can take some toolsets that you need, compose the toolset that you need, and you can orchestrate some functions. And all the NSs that are deployed, they have the templates and they have the instantiation that is there of NS. So, you know, we have we can do some, from the CCF, we can trigger some migrations if the configuration of resources will change. Then finally, we have for sure the CCF optimization functions, because as I said, the resource pool is dynamic, it can change. And we have some management observing, you know, the portals for the operator, for the customers, CCF management functions, performance analysis, and such issues. And you see our extended version of NS with the management and service orchestrator. The resource orchestrator is as usual in a cloud. It means in a CCF it is reactive, but you will have also proactive resource allocation, function migration, deployment. And this is the role of service orchestration that is data-driven from a classical management system. As I said, this is specific for each NS to cope with scalability. And there is also part of the management and orchestration that is generic for all NSs. It is master manager and orchestrators, and in short, assets database that keeps everything what can be used. So this is quickly about the concept. You will find a lot of in work package 2, work package 4, and work package 5 deliverables. And actually, I will hand over to Robert, who will tell you a bit about the implementation, because we were able to implement the concept.
Yes, exactly. Good morning. Next slide, please. So here you can see the basic implementation. In this implementation, we focused mostly on CCF components and functionalities. So essentially in PoC, we actually deployed the 6G-Cloud framework over 2 data centers. Both data centers utilize OpenStack. The CCF framework contacts with those 2 OpenStack instances via the dedicated Vim adapter. To implement this adapter, we use the industry-grade tools for infrastructure as code. So this includes Terraform for the infrastructure configuration and networking setup at low levels, and also Ansible, which basically SSHs into virtual machines and setups the configuration, install some components, make the configuration of the virtual machines, and also install all of the components that are needed by the resource partition. When it comes to the CCF, the majority of components are implemented with Python and fast API for the SBA, so for service-based architecture and communication between those. We use Kafka as the message broker, and a lot of databases, which are mostly implemented with MongoDB. And also we use Minio, which is used to store some of the manifests and things that are less structured than regular JSON files. When it comes to the resource partition itself, this is actually, I would say, a composition of several Kubernetes clusters. These clusters are interconnected with Cilium mesh. So essentially, we want to establish the global communication with the global DNS between several clusters, and that's what Cilium is for. When it comes to the management, we want also to have the control over how we deploy the individual resources and how we split the network service across many clusters. And to this end, we are using Karmada, which also introduces something that is called the propagation policy, which enables us to actually control which resources are deployed where. In order to make a centralized access, we also use Thanos, and this is the component that integrates several Prometheus databases and provides a single exposure point. And also in this context, it is important to have this very single exposure point to expose to the MOF, so that we do not need to access individual clusters to pull any kind of metrics for the optimization and management of the network service. When it comes to MOF, we stick to a very, very basic implementation, which is really about the service orchestrator and RPRs. These are components that are used to deploy the network service and also to issue the requests to deploy the resource partition. Next slide, please. Here you can see the overall stack. As already mentioned, the more details are in deliverables and in the full demos on the YouTube channel. What I would like to add as an addition to the previous slide, we also implemented a simple CI/CD, which is mostly targeting the AI MLF in the framework. And essentially, this CI/CD pipeline is using GitHub, Docker Hub, and Flux CD. As you are seeing that the GitOps paradigm is really getting more and more popular, so wanted to also leverage this paradigm here in 6G-Cloud. Maybe one more word about the observability here. So for the each cluster actually deploys a set of the REST toolset, and this REST toolset uses the Prometheus stack. So we are having the resource monitoring, the physical resources monitoring of individual nodes and pods. And also we deployed the Kepler, which is the tool that is used for the energy consumption estimation. Additionally, we deployed Hubble, which is like, I would say, an inbuilt feature for Cilium, and it enables us to track the flows between individual pods and also get I would say, the flow level information on the exchange between individual components of the whole REST and the service that is deployed over it. Next slide, please. Okay, so regarding the demo, we implemented 4 basic procedures. These include the REST creation, NS deployment, NS migration, and IAF change. So essentially, the first one is about creating the physical resources and configuring those. This includes the setup of Kubernetes clusters and Karmada. The NS deployment is about actually sending some manifests to Karmada API, including also the policy propagation to deploy the NS across the integrated and connected clusters. The third one, the NS migration, is about changing the policy in order to see how the NS components get migrated from one cluster to another. And the last one includes actually the deployment of the dedicated AI function that is for the prediction of some KPIs. And when the quality of this function degrades, the automatic retraining of the function is triggered, and also the update of it. So there will be shown a whole pipeline of how it works. Okay, so let me now share my screen. Okay, so starting with the demo, as you can see, the full demonstration is available on our channel. So the first step is REST creation. Here is the overall procedure of how it works. So essentially, the MOV operator is going to request the creation of REST, and after that, CCF is going to handle all of the logic to establish the resource partition. So first, we issue the call over the API, which actually contains only the type of the NS that we want to deploy. And as you can see, after the API call, we are getting a lot of different outputs. These outputs essentially relate to the creation of the infrastructure with Terraform. So it takes a lot of time, so it's speeded up. So after some time, we've got the infrastructure created, and after that, we have the Ansible inventory generation. And as you can see now, the playbooks are being executed, and these playbooks essentially configure the nodes. And also, download some packages that are necessary for Kubernetes installation and also Karmada. So as I mentioned, it takes a lot of time. The whole process actually lasts about 30 minutes, which is a very long time. That's why the video is cut so much. Nonetheless, after the whole process, we can investigate the messages in CAFBAT that have been exchanged. So essentially, you can see some messages like the notification about the start of creation of RESP that is delivered back to MOF, and also the status. So once everything is done, you can see that all of the information that is needed to get into the clusters are handed over. So some certificates, some endpoints, and so on. As you can see, there is a lot of this data. I do not want to really stick to details, but this is essential to actually convey this data in order to be able to access the clusters and manage these from the MOF level. All of this data is obviously persistent, so we store that in dedicated MongoDB database. Okay, so going to the components that got deployed, we SSH into the nodes, and you can see that for the both clusters, we have a lot of components deployed. This involved the Karmada operator, Karmada components, also things related to Cilium and cluster mesh. There is also Kepler and other components that are responsible for monitoring. I would say the final step for verifying if everything is correct is to check the cross-cluster connectivity. And in order to do that, we can just call Cilium to check the status. As you can see, both clusters are operational, and also we have the app state of the cluster mesh. So there is good connection between both of the clusters. The last point I would say is checking if Karmada control plane actually sees both clusters. And here we can see that both are ready. So we're good to go to deploy the network service. So again, here is the whole procedure. I would say that I don't want to get into details here. Those details are in our 6G-Cloud YouTube repo. Okay, so what we start with is that we start with first of all, typing in the RESP ID. This is the unique ID of the resource partition that we created. And also we define the NS type to be deployed. As you can see, after some time, we get the response, the positive response that the NS is deployed. As the feedback, we get the namespace. So this is like the unique identifier for our NS. As you can see, there are already some services deployed. Also, the propagation policy that has been applied. In this case, this is multi-cluster, so we will be able to see pods that are spread across two clusters. And as you can see, in the second cluster, we've got IEF deployed, and in the first one, there is the NS. As the final step, we check the status of the NS, so we just use the exposed APIs, and then as you can see in the response body, it's working and it's operational. So now going to migration. So again, we will be interacting with Karmada to apply a new propagation policy and to move all of the components to a single cluster. So in order to do that, we just select again the network service ID. And after that, we apply the policy, which is going to be a single cluster policy. Here you can see how this policy actually looks like in configuration. So once we execute that, it takes some time. We get the response that the migration is successful. So on the left, you can see the actual API calls and the information that is processed by the service orchestrator. In the top right, there will be, again, the cluster information from the cluster one. And here you can see that both of the components are already deployed, so they migrated. When it comes to the second cluster, you can see that the AIF pod is in termination state. So essentially, it's just, and now it's actually removed. So it took some time to move from one cluster to another, but the migration was successful here. And again, we check the status of the NS, and here you can see that the policy has been updated when it comes to NS, because it's now a single cluster. And moving to the last part of this demo, which is AIF change. So this one would involve some more components, because in addition to I would say regular framework, we're also going to use Flux. So a couple of words about NS. So NS in this case is essentially the component that emits the link utilization data. So this is, I would say, a very simplified one. That link utilization data is used to predict the next samples by LSTM predictor, which is embedded inside AIF. Both inputs are observed by the AIF observer, which actually computes the drift. And based on the drift, it triggers the update of the AIF image. The image is then pushed into the image registry and actually automatically pulled by Flux controllers. So here you can see the actual logs from NS, AIF, and observer. So we will start by investigating what is happening inside MLflow, which is our tracking server for this experiment. So for now, you can see that it's totally empty. When it comes to the registry, we have only one image with tag 1010. Again, this video is accelerated because it takes some time to actually go through the samples and detect the drift. You can see the actual drift detection right now in MTOU component. And this drift detection triggers the AIF trainer. You can also see it at the bottom of the screen that some information regarding training is pushed to the MLflow server. Once the component, the model is trained, we are actually moving to building the Docker image. And you can see that Docker builder is already executed. It takes, again, quite some time. And once all of the libraries, all of the components are built, we are actually pushing the Docker image to Docker Hub. If we go again and check, you can see that the new image has been pushed just a minute ago. And at the same time, you can see that once this image is pushed, Flux controllers detected the change. And the agents that reside in the cluster perform the CI/CD and deployed the new AIF with the updated model. So again, it takes some time to deploy and to substitute the image, but as you can see, it is successful. Going back to the training runs in MLflow, we can see that there are some updates regarding the training process of that LSTM predictor. Here you can see some training validation and validation loss. Okay, as the final step, we get back to GitHub, and here you can see the automated change of the image that has been triggered by the NTOU. Okay, so that's gonna conclude the implementation and demo part. So thank you very much, and I hand over back to Sławek.
Okay, thank you, Robert, for a very nice and quick presentation. So the final slide from our side. So first of all, we are happy because we were able to integrate. It was like a new concept, very disruptive, completely different than what actually is existing. We were able to find tools that can be used for that. We were very happy with Terraform, with Ansible that provides us infrastructure as a code. But we noticed that due to Kubernetes specific issues, it's not one-to-one mapping between the reference architecture and the implementation. And there can be, by the way, different implementations. And the next presentation will be about something a bit different. We already implemented KPI-1, that is energy efficiency by cross-framework operations, in short function migration. So you have seen the mechanism of migration. Actually, you see some results that we will present next week at IEEE NetSoft conference. And as you see, we have some positive results, about 30% energy saving using simple algorithm, because we tackled with some technical issues with NS that we used. On 6G-Cloud channel, on 6G-Cloud YouTube channel, you will find much more information. There are also deliverables. And this testbed will be used for validating of 2 more KPIs. The first one will be pretty simple about the aggregation of resources gain, and we do expect it should be more than 30%. It is already advanced, and we are very close to that. And also service orchestration efficiency increase by the use of AI orchestration, using AI orchestration, driven orchestration. So you know, these are just two more KPIs that we are just trying to implement and have some results. We will publish more papers from the results that we will obtain. So because of the time constraints, we are several minutes late. I will now ask Jesús from University of Murcia to present its implementation that is focused on just on AI, on some other on AI and orchestration. So I think it's nice complementary talk to ours. Jesús, the floor is yours.
Okay. Thank you, Sławek, and hi, everybody. This is Jesús Pérez Valero from the University of Murcia. And in this webinar, I'm going to present a proof of concept demonstration on service interruption prevention via dynamic auto replacement of AI/ML models. Just to let you know that, as Sławek previously said, they were focused more on the CCF part, and our work and the work that we are going to present here is more focused on the MOF part, on the management and orchestration part. That said, basically our demo will highlight many interaction among the different components of the 6G-Cloud architecture. Here we have a full picture of the 6G-Cloud architecture. Many of these components have been already explained by Tao and Sławek, but our scenario basically is a dynamic auto-update use case that demonstrates the capability of the MOF to automatically request an AI/ML model retrain from the AI/ML framework when anticipating an SLA violation. Upon successful retraining, the AI/ML framework automatically deploys and seamlessly replaces the updated model within the network service orchestrator. This is done also without any service interruption. This zero downtime model update is validated in our Gaia testbed. Basically showcase the architecture ability to continuously evolve into embedded intelligent based on real-time operational data that is gathered from the CCF, enable a fully autonomous and resilient scaling operation in a 6G-Cloud network environment. I wanted to explain the components in detail, but many of them has been explained by Tao as the network service. As you can see, the network service is a component inside the MOF and is basically responsible of handling the network services. Then we have the service orchestrator that you can see that is a component in green inside the network service director. And basically is the responsible for the intelligent and autonomous lifecycle management of the specific network service. Then we have a new component, what we call the network function manager. You can see it as a red box inside the network service instance. And basically it acts as a bidirectional bridge, translating high-level orchestration commands from the CCMF into a specific actionable instruction for the run network function, NF. Then we have the CCMF, as you can see, is a component inside the service orchestrator. And basically, it's a component that embodies the functionalities of the all-run service management and orchestrator framework, providing a dedicated, it provides a dedicated interface for managing and orchestrating the radio access network domain alongside the core network services. Then we have the network service instance itself, which is a logical entity which is deployed, managed and orchestrated within the MOF. Then we have the AML framework, which is in the right side of the figure, which basically provides foundational capabilities to design, train, deploy, and continue to manage the AML models. And finally, at the bottom of the figure, we have the CCF, which has been already well explained by Slavek. And basically, it's the component that unified all the infrastructure substrate that abstract and manage the heterogeneous computing resources across the cloud continuum. Okay, the use case that we want to show is going to be instantiated in our Gaia lab testbed. Basically, this testbed is located in the computer science faculty at the University of Murcia. Its main research purposes are focuses basically on the area of 5G technologies. We have some equipment that fulfill all the requirements of 5G testbed, as we have a core network components. We have different SDNs, software-defined network function virtualization, and so on and so forth. We also acquired a core from the Amaresoft with all the associated RAN hardware, and both cores has been fully integrated into the testbed. Okay, now we are gonna have a look at the specific technologies that we use to build this system. We have basically 5 main building blocks. First, for the resource layer, for the CCF, we basically use Fluidos, which is a platform for the resource orchestration decision, and it acts as our resource manager. Basically, Fluidos, it handles things like creating some resource partition and it interfacing with the VIN and network function virtualization infrastructure. Second, for the MOF, which is the brain of the architecture, it runs basically as containerized pods in Kubernetes and is responsible for the service lifecycle management, the service orchestration, and drives the decision making for our use case. Third, we have the AML framework, which basically is built on Kubeflow. This is also done in collaboration with our partner, FDI. Basically, Kubeflow is a popular MLO platform. It provides essentially pipelines for training, tuning, and serving the AML models to the MOF. Then we have the network service itself, which is made of 2 main platforms, SRES-RAN and Open5GS. This network function basically, this network function basically are continuously monitoring and managing through the network function manager that we explained in the slide before. Finally, to glue everything together, we use Eclipse Xenot for all the communication between the different components, and we also use Prometheus, Grafana, and Kepler for monitoring and the energy consumption tracking. Okay. Now let's take a slightly deeper look at the implementation. Here you have a figure with all the components that involve our implementation. In the top part of the figure you have the MOF. In the bottom part of the figure you have the CCF, and in the right side of the figure you have the AML framework, and also all the technologies that built these components. First, it is worth to say that we have adopted a cloud-native approach. That means that every single architectural component runs as a native Kubernetes pod, which give us the benefits of the scalability and resilience. Also, to keep things clear and clean and manageable, these pods are organized in 3 different and isolated namespaces. That means that we have one namespace for the CCF, another one for the MOF, and the last one for the AML framework. As I said, for the communication between all of these components, we have implemented Eclipse Xenode. Specifically, we use two main primary patterns, which are the query and reply for the single interaction, and the publish and subscriber for long-lasting interaction. Okay, and the figure basically illustrated the relationship between the communication buses and the different components. As you can see, we have a Xenode communication bus between the resource, the databases and the network service director, and the components that are below. That means that the CCMF, the master service orchestrator, the service orchestrator, and the AML framework. We also have a Xenode communication bus to interact between the CCF and the MOV, and also another one here on the right side in green, which communicates with the AML framework. Here we depict a simplified version of our demo that we will sound later in the form of a workflow diagram. First, as you can see in the MOV, the process starts with some monitoring agent that collects metrics such as CPU usage and the other key performance indication from the network function. Then this information is then processed in the service orchestrator, which executes a pre-trained AI model to detect an SLA violation or service degradation. Once the MOV detects an SLA violation, it triggers the network service director, which requests the AML framework a new retraining request. So you can see here that when in the figure that when the service orchestrator detects the violation, in the step 1, it requests a model retraining to the AML framework. Then the AML framework retrieves the latest available data from the monitoring database and train a new model based on that data. Once the training is done, the AML framework sends the model to the MOV, which deploys the new model for online prediction. Now we are gonna explain more in detail the different interaction among the different components in the demo scenario. Starting from the bottom of the figure, as you can see, the CCF includes a physical infrastructure layer which contains user equipment served by radio units. First, some monitoring agents basically are deployed at the edge and the cloud servers and collect infrastructure metrics such as CPU. These metrics are basically extracted from the network function manager. You can see here in the step 1, and are forwarded to the MOV in order to be stored in the monitoring database. Once the CCMF, which is the component that you have here inside the MOV in green, receive the updated network service metric, see the step 2, it publishes them through the Xenode router, allowing the monitoring database to subscribe to the corresponding topic, store the metric, and make them available to the network service director. See the step number 3. Then the network service director then combines measure network metrics with the service level objectives defined in a service level agreement to generate a consolidated service view and send it to the service orchestrator. See step number 4. Then the service orchestrator then use a machine learning model to predict the performance degradation or KPI violation and notify the network service of the outcome. If the service orchestrator predicts a KPI violation, it immediately raises a performance degradation alarm, which triggers the network service director to request a model retraining operation from the AML framework. See the step number 5. Through an interaction cycle, the AML framework retrieves data from the monitoring database. You can see it in the step number 6, and used the most recent updated data set to retrain a new prediction model. Then the collected live data is used to build the training pipeline within the AML framework. See, for example, the step number 7. resulting in a retraining and updated forecasting model. See the step number 8. Then once the new model is available, the network service director receive it in step number 9 and enable its deployment so that the service orchestrator can update its local inference engine and use the latest model for online prediction. You can see it in step number 10. In the following slides, we are going to present a demonstration of how this use case works in our Gaia testbed.
For this demo, we assume that all the architectural components have already been deployed. Within the network service, a virtualized UE and GNB are connected through ZMQ to enable communication between them. In this setup, the UE continuously generates traffic, while the Network Function Manager is responsible for collecting monitoring metrics from both the GNB and the 5G core. As shown on the screen, the monitored metrics include key indicators related to radio cell status, the number of connected users, uplink and downlink throughput. Moreover, it has also monitored metrics related to signal quality, such as SINR and packet error rate, as well as infrastructure resource utilization metrics such as CPU and memory consumption. As previously explained, the Network Function Manager forwards all these monitoring metrics to the CCMF, which is responsible for storing them in the MOF monitoring database and making them available to the Network Service Director, allowing it to access real-time metrics. Once the Network Service Director retrieves these metrics, it forwards this information together with the target KPIs defined in the SLA to the Service Orchestrator. The Service Orchestrator runs a machine learning model in real time to predict potential KPI violations or service degradation in advance, thereby enabling proactive decision-making before the service is affected. If the Service Orchestrator detects a potential future service degradation, a trigger is activated to notify the NSDIR of the corresponding decision. At the same time, a request is initiated to the AIMLF for a new model retraining process, allowing the model to adapt to the updated conditions of the network service. Once the request for a new model has been initiated, the AIMLF retrieves updated monitoring metrics in order to retrain the model using the latest network service data. The AIMLF collects updated radio and infrastructure resource metrics, including CPU and memory consumption, from the monitoring database over a 30-second period. This process allows the system to build an accurate and up-to-date dataset for retraining the new model, thereby improving the accuracy of future predictions. The AIMLF retrains a new model using the collected dataset and generates the corresponding binary artifacts, encapsulating all relevant information needed for deployment and inference. The AIMLF then sends a retrained model to the Network Service Director, thereby completing communication flow with the AIMLF. As can be seen, the NSDIR forward the retrained model to the Service Orchestrator. At this point, the Service Orchestrator will use this model to predict potential future service degradations. As anticipated by the predictor, an increase in CPU consumption was detected and correctly forecasted. As we can observe, the CPU used by the UE has increased significantly, reaching nearly 5 cores. This confirms that a predictor successfully identified the upcoming service change, enabling real-time adaptation and continuous model improvement. Thank you for your attention.
Okay, so that's all from my side. Thank you very much for your presence, and I will give the token back to Tao.
Okay, thanks, this three speakers to give this nice introduction about the demo. Yeah, so thanks everybody to participate in this webinar. So we have still 2 webinars to go for other 2 PoCs. But today, that's a very good webinar, and I hope you also learn something from our project. And also we have this channel to video channel, YouTube channel, and also LinkedIn channel to share off information. If you want to know more, you can go for there to check. And also we will publish our webinar recording in our YouTube channel later on. But that's Okay, so that's all for the webinar. Thanks everybody. So let's have a nice day for today, and bye bye.